All right, so now the next step is going to be assigning priority to those different groups, right? Remember the whole, how do you spot a chiral molecule? It has a stereocenter. What is a stereocenter? It's a carbon that's bound to 4 different things. So now we're going to look at those 4 different groups and we're going to assign priority to them, meaning we're going to rank them 1, 2, 3, 4. This is an important skill that we're going to, again, be using in our classification system. This is the first step that we're going on here is, this is just what this lecture is. Everything else will be done in the 3rd lecture. This is what we're going to focus on first, is just assigning priority to those 4 groups. So let's see how this is going to be done. Okay, so again, you're going to start out with something like this, right? Do I have a stereocenter? Hopefully you were able to pinpoint that this carbon right here is indeed bound to 4 different groups. And one of those different groups is this hydrogen that's implied, right? So it's not explicitly drawn in. Okay, so the first thing we're going to do, so these are my 4 different groups here that are attached to this molecule, right? About its stereocenter. And again, I'm going to assign priority to this group. So there are going to be a set of rules that we're going to learn for this. The first rule is that the higher the atomic number, the higher the priority, or I guess really the lower the priority in terms of it would be priority 1. Okay, I guess you would number, I don't know. Anyways, high priority means 1. Okay, so here I can assign priority to each one of these groups. Which one has the highest molecular weight? That would be the chlorine. Which one has the lowest molecular weight? Or I'm sorry, not molecular weight, atomic number. That would be the hydrogen, sitting all the way at 1. All right, and then carbon versus oxygen. Oxygen has a higher molecular weight, higher atomic number than carbon, right? So in terms of priority, this is how I would assign a priority to this molecule here. Okay, and what we're gonna do with this priority, we'll see in the next video, but assigning priority is really what we're learning here. All right, so if they're all different atomic numbers, awesome, done. But what happens in, for example, this molecule here? I'm going to run into this tie situation, right? So first of all, I have oxygen. That's obviously got the highest atomic number. That's going to be 1. I have hydrogen. That's got the lowest atomic number. That's going to be 4. But what about these? These are both carbons and carbons. So that means we got a tie on our hands. So what do we do there? Then we're going to look at what those carbons are bound to. So on this carbon here, oh, giving the punchline away. On this carbon here, it's bound to an oxygen and 2 hydrogens, right? There's a hydrogen implied here and a hydrogen implied here. And on this carbon, it's bound to just 3 other carbons. And then you go back to rule 1. Which one has the higher atomic number? So in this case, this oxygen compared to this carbon is our tiebreaker. Okay, that would mean that this group is priority 2 and this group is priority 3. Notice that you're just looking at the atomic number of whatever the highest, whichever one is the highest atomic number in the 2. So it's not like you're taking them and adding them up or anything like that. It's just simply comparing the atoms. In this case, it's an oxygen and a carbon. Oxygen wins. So there, we're done. Okay, so assigning all the priorities. Again, this one would be 1, 2, 3, and the hydrogen's 4. Okay, so now what if you have a tie in that respect as well? So again, let's look at this example here. We have this oxygen is again going to be priority 1 because it's got the highest atomic number. This hydrogen is going to be priority 4. It's got the lowest atomic number. But here we have a tie. These are both carbons. But not only that, they're both CH2s, right? So they're both bound to 1 other carbon and 2 other hydrogens. So again, we just have a tie. So what do? You're going to go to the next atom. Go move 1 down the line here. Right, so originally I was looking here and here. There was a tie with everything. So now I'm just going to jump over 1 this way and over 1 that way. Look at what's being bound there. So here we have a carbon that's bound to 2 carbons and a hydrogen. Here we have a carbon that's bound to 1 carbon and 2 hydrogens. So here is my tiebreaker right here, the comparing this carbon with this hydrogen. So that's why this would get priority 2, and this gets priority 3. Okay, so just filling in everything again. This is 1, this is 4. Okay. And then the last rule we have to cover is what to do about double bonds. So when you see a double bond, you're going to count it as if that atom is bound twice, right? So in terms of looking at this carbon here, and I have to see who's it bound to, I would consider it to be bound to 2 oxygens and a hydrogen. That's what that double bond means, right? So this double bond here is why I have 2 oxygens in this list. So we can just go through and do this example. Where's my stereo center? Hopefully you guys have identified that. Boom. Okay, and now I have carbon, carbon, carbon. So to a first approximation, it's all a tie. Then I'm gonna look at what those carbons are bound to. Here we have CH, H, here we have CH, H, and here we have H, 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 and here O, O, H. Okay, so right off the bat, I can assign priority 1 and priority 4. Priority 1 is going to go to this carbon right here because it's bound to that oxygen. And priority 4 will go to this carbon here because it's only bound to hydrogens. Now I have a tie between these two, so what am I going to do? I'm going to jump to the next one. This carbon is bound to a carbon and 2 hydrogens. This carbon is just bound to 3 hydrogens. So that's why this group here would win. It gets priority 2, and this one's 3. Okay, and it's this whole group that has that priority, right? So that's 2, that's 3, et cetera, et cetera. Okay, we can do another practice here. So first of all, where are my stereo centers? Stereo center right there. What about this carbon right here? Is this a stereo center? No, because it's got 2 methyl groups, right? 2 of its bonds are the same, so it is not going to be a stereo center. There's only 1 stereo center in this molecule. Also, this isn't going to be here because it's not sp3 hybridized, right? So double bonds don't have the stereo center. You have like a cis-trans thing you might have to worry about with double bonds, but there's not going to be any chirality. Okay, so now we're going to look here. So first of all, it's missing something in the drawing. That would be this hydrogen. Hydrogen's got the lowest number, that'll get priority 4. Chlorine's got the highest atomic number, that will get priority 1. Here I have a carbon, and here I have a carbon. That's a tie, so now I gotta look at what they're bound to. This carbon over here is bound to a carbon, and a hydrogen. What about this carbon here? So it's bound to 1 carbon down there, and then it's got a double bond to another carbon. So that's as if it was bound to 3 carbons. Okay, so that's why this one would get the higher priority. This gets 2, and this gets 3. Okay, so now what in the next chapter we'll use these priorities in order to assign that R and S designation of a chiral molecule. Before we do that, we're going to sort of take a step back and talk about alkenes again. I said that they don't have any sort of a chiral aspect to them, but they do still have this kind of cis-trans thing that we've seen, right? Larger alkenes actually cannot be classified as cis or trans. You have to have a vinyl hydrogen, meaning a hydrogen has to be bound to both of these carbons, these vinyl carbons, in order to be able to get a cis and trans designation. So what about this down here? Right, so this vinyl carbon does not have a hydrogen on it, so we can't classify it as cis and trans. Instead, we're going to use this EZ designation, okay? E is kind of trans-like, meaning that the highest priority groups are on the opposite side of the double bond. The Z isomer, the high priority groups, are on the same side. And so I like to say they are on Z same side as a good way to remember the EZ designation. Okay, we had to learn about priorities before we can actually assign EZ, so that's why it's in this lecture. What you're going to do to assign an EZ designation, so first of all, maybe you can kind of see that this is more trans-like in how it looks, but again, we're not allowed to classify it as a trans because it doesn't have a vinyl hydrogen, because it's missing a vinyl hydrogen. So how do we assign EZ designation? What you're going to do is chop your double bond in half, and then you're going to look on one side and you're going to assign high and low. Which one has the higher priority? So this, we're missing this hydrogen that's implied. This is a carbon. Carbon has a higher atomic number, so this is going to be my high priority group. This one's my low priority group. And now we're going to look on the other side of our double bond and assign high and low, right? So here we have 2 carbons, but one of them is attached to 3 hydrogens and the other one's attached to a carbon and 2 hydrogens. So this is my high priority group. This is my low priority group. And notice that my high priority groups are on opposite sides of that double bond, right? So this would be an E stereoisomer. In contrast, let's look over here. So again, what you got to do is chop your bond in half. Use the same color. Chop your double bond in half, assign high-low on one side, and then assign high-low on the other side. So which one is going to be the higher priority group here? So first approximation, I have carbon and a fluorine. This fluorine is my high priority group. This carbon is my low priority group. Now I'm going to jump on the other side, and again, this is high, this one's low. So again, these are your high priority groups are on different sides of your double bond, right? Here's my double bond. So this is again going to be the E stereoisomer. Notice that it doesn't matter at all that this group is higher in priority than this group, right? You're only chop the double bond in half, assign on one side and assign on the other side. And then just for completion, we'll take a look at an example of a molecule that has Z stereoisomer. Okay, so that would be like if I put something like a chlorine down here, right? So this was high, we already went through this. This one was high and this one was low. So over here now I would compare chlorine with carbon. This one's high and this one's low. So now my high priority groups are on Z same side, so they get the Z designation. Okay, so this is very similar to the cis-trans concept. It's just kind of building off of it for more complicated alkenes. Again, it was in this chapter because you need to be able to assign priorities to be able to assign EZ stereoisomer designations. Okay, so now we're going to move on, practice that assigning skill, and then we can move on and put it all together to designate chiral molecules as either R or S.